Hello class, this is the ENGR 359 lecture for October 6th, lecture number 13. Unfortunately, I forgot to press the record button when I gave the lecture this morning, so I'm redoing the lecture now in a shortened form so that I do have something that I can post on YouTube. So I apologize for not recording this morning, but I'm going to basically give a summary of what I talked about in lecture this morning, October 6th. So we're currently talking about the ARM processor and some of the instructions in it, and we left off at this point on Monday. We're going to work through this example of some ARM code. You can find this ARM code in Appendix D of the textbook, as well as a very good explanation of it, but we'll go over it here as well. So in this particular little section of code, we're basically going to read the ASCII codes of two characters, and we're going to convert those ASCII codes to what we call binary coded decimal, and then pack the binary coded decimal versions of these two characters together into memory into 1 byte. So if we talk about the characters on your keyboard from 0 to 9, so 0, 1, 2, all the way up to 9, binary coded decimal just means a binary bit pattern, and it's a 4-bit pattern to represent each of these decimal digits in a 4-bit binary pattern. So obviously the BCD for 0 is going to be 4 zeros. The BCD for 1 is 0001, for 2 is 0010, all the way up to 9, which is 1001. Okay, so each of those 4 bits is what we call the binary coded decimal representation of the decimal digits 0 to 9. Now it just so happens that, well, it's not coincidental, it was intentionally made the case that when the ASCII codes were developed, these 10 decimal digits do have an ASCII code each, and that ASCII code consists of 7 bits. It is such the case that the least significant 4 bits of the ASCII code for 0 are all zeros, and that the 4 least significant bits for the ASCII code for 1 are 0001, for 2 are 0010, etc. So it's convenient that the least significant 4 bits of the ASCII code for any one of these digits is the binary coded decimal representation for that digit. Okay, so let's take a look at the code and see what we got here. The first instruction is a load instruction, and this is an example of a pseudo instruction, and I've talked about pseudo instructions before, and you can find more description of pseudo instructions in Appendix D of the textbook. But we're going to use a load instruction to load a register with a value, and the value we want to load it with is the address LOC. So LOC is a location in memory. And so up here I'm going to draw a 32-bit memory word at the address LOC. Okay, and I'm not going to draw the individual 32 bits, just the 4 bytes that make up that memory word. And let's assume that the address, we've got byte addressable memory, so every byte in memory has a unique address. So let's assume that the least significant byte of this word has the address LOC, the next one has LOC plus 1, the next one has an address of LOC plus 2, and LOC plus 3. Okay, so the typical byte addressable memory where a memory word is 4 bytes, each one of the bytes in that memory word has its unique address, LOC plus 1, plus 2, and plus 3. Okay, let's assume that in the byte LOC in this memory word, we've got the ASCII code for character 1. And in the next least significant byte in this memory word, at address LOC plus 1, we've got the ASCII code for a second character. Okay, so we can assume that that's what's in memory when this program begins. Okay, so the first thing that we do is this instruction is going to take the memory address LOC, which is the address of this least significant byte in this memory word, and the equal sign tells the assembler that this is not a small number, this is an actual address. Okay, and this address is going to be loaded into R0. So R0 will now act like a pointer. R0 will hold a memory address. It'll hold the memory address LOC. Okay, and you can read more about why this is a pseudo instruction in the appendix D of the textbook. But all we need to know right now is that when we have an equal sign, that tells the assembler this is a big address, and you're going to put that address into R0. And this is a very common way in ARM code of moving an address into a register R0 like this. Okay, so now R0 has this address LOC in it. It's a pointer. The next instruction is also a load instruction, meaning get something from memory, but it's got a B at the end, meaning load a byte. So it's only going to load 1 byte into register R1. The effective address of this byte is the contents of R0. Okay, so this is the pre-indexed addressing mode in the ARM processor with no offset, okay, or a 0 offset. So this instruction simply means go to the address that's stored in in R0, which is LOC, which is the address for this word, which is the address of the lowest byte, the least significant byte in the word. Go to that address and take the byte that's there and put it into R1. So it's going to read this ASCII code for character 1, which is that address LOC, and put it into R1. So down here we'll draw R1. So R1 is a 32-bit register. I'm just going to show the 4 bytes that it's made of. Okay, and so load register byte is going to take the byte that's stored at LOC, which is in R0, and it's going to take this byte and it's going to put it in the least significant byte of R1. So the ASCII code for CAR1 goes there. And these will all be zeros. Okay, so that's what the second instruction does. The third instruction is similar. It's again load a register, this time load register R2 with a byte, and the effective address of that byte is the contents of R0, which is still LOC, plus this offset of 1. Okay, so the effective address now for this instruction is LOC plus 1, which is the address of this byte, which holds the ASCII character for the ASCII code for character 2. So this byte of information at LOC plus 1 is going to be put into R2. So the ASCII code for CAR2. Okay, so that's the end of the third instruction. The fourth instruction is an AND. It's a logical AND instruction, so it does a bitwise AND of what is currently in R2, which is this, and again, these are all be zeros. Okay. So it's going to take what's in R2, which is this, and it's going to AND it with the immediate operand of hexadecimal F. So the ampersand means hexadecimal, so we're dealing with the hexadecimal number F, which is 15 in decimal, and we're going to AND that bitwise with what's in R2. Okay, well, what is the 32-bit representation of hexadecimal F? Well, F is 15, which means the least 4 significant bits are ones, right? So that'll give us 15. 1111 is equal to 15, which is equal to F in hexadecimal, and all the rest will be zeros. Okay, so this AND instruction is going to take this, what's in R2, and it's going to AND it with this immediate operand, hexadecimal F, which is all zeros except for the last 4 of the 32 bits are ones. Okay, so obviously when you AND zeros with anything, all of these zeros, when we AND them with anything else, we get zeros, including the top 4 bits of the ASCII code for character 2. Remember, this is 1 byte. The ASCII code is actually 7 bits. So we're only interested in the last 4 bits of the ASCII code because we know those last 4 bits correspond to the binary coded decimal representation of this character. So we're only interested in the last 4 bits here. So we AND everything else, the top 28 bits of this 32-bit register, we AND it with zeros. So there's 28 zeros here. 29, 30, 31, 32, the last 4 are 1s. Okay, so that's going to clear anything that's up here. It's going to clear to zeros when we AND it with all of these zeros, but these 1s mean whatever we have here we're going to end up with. So if we are dealing with the character 9, then the least 4 significant bits in register 2 would be 1001 if we've got the ASCII code for the digit 9 in there. So when we do this bitwise ANDing, well, 1 and 1 gives you 1. 0 and 1 gives you 0, 0 and 1 gives you 0, 1 and 1 gives you 1. So we end up with the BCD representation again. So by ANDing with this pattern of 1s, just gets rid of everything else or clears everything to 0 above the last 4 bits. Okay, and then we put that back into R2. So now R2 will be the same, except these will definitely be zeros. And these will all still be zeros. Okay, so now R2, we've got the BCD version for the digit 9 in R2. Now the last instruction is OR. ORR is logical OR. So again, it's a bitwise OR. So we're going to OR what's in R2, which is now this, with what's in R1 shifted to the left 4 bits. Okay, logical shift left 4 bits. Well, this is what we got in R1. So if we've got, let's say R1 has the ASCII code for 2 in it. I don't remember what the 3 most significant bits in the ASCII code for 2 are. Let's call them X, 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 and then we would have 0, 0, 1, 0 if we were storing the ASCII code for 2 in register R1. And this would be a 0, and then all of these are zeros. That's what we've got in R1. Well, now we're going to OR that with what we've got in R2. Okay, so we've got this in R1, we've got this now in R2, and we're going to do a bitwise OR. So what are we going to get now? Well, pardon me, we don't do the OR yet. We have to shift what's in R1 first. We have to shift it by 4. So that means all these are all zeros, but these 8 bits get shifted to the left by 4, which means that R1 will now hold 0, 0, 1, 0, and the X, X, X will be up here. Okay, and we shift in with empty zeros. So we've shifted this ASCII code in R1 to the left by 4 bits. So now this is what we've got in R1. And of course, these are all zeros still. So now we're going to OR this with this. Okay, and when we get that, what are we going to get? Well, these are all zeros, these are all zeros, and we're going to be left with this ORed with this is going to give us this, and these zeros ORed with this is going to give us this. So we're going to end up with, if I can erase this, we're going to end up with 1, pardon me, 1, that's not what I want either. We're going to end up with 1, 1, 1, 1, and then the 0, 0, 1, 0 up here ORed with this gives us 0, 0, 1, 0. We're going to end up with that in the lowest byte, and that's going to get put back into R2. So then this is what we've got in the lowest byte of R2. So notice what we have now. We've got the BCD representation for the digit 2, and the BCD representation for the, I'm sorry, not 111, it's 1001, pardon me, because we're ORing this with this up here. So it's 1001 ORed with zeros gives us 1001, and these zeros ORed with these bits 0010 gives us 0010. So we've got the BC representation for 2 in the upper 4 bits of this lowest byte, and we've got the BCD representation for 9 in the lowest 4 bits of that byte. Okay, and then we're going to store that. The last instruction here is a store instruction which says take what's in R2, but because of this B, it's going to take just the last byte, which is these 8 bits. It's going to store that byte into some memory location called packed. Okay, so we started off with the full ASCII code for these two characters in memory, and we end up at some other memory location having just the 4-bit BCD codes for 2 and 9 in the byte. Okay, so that was the purpose of this little bit of code, but it's just an example of more ARM instructions. Okay, we started with this example. Let's move on and look at a few other instructions. We've got what we call the load and store multiple operands. Many times we have a bunch of data in memory, one memory word after another, and we want to load all of these words, these memory words, into separate registers. Well, we could do that one register at a time with just a simple load instruction, or we can use the load M means multiple, IA means increment after. We'll talk about that in a second, but LDM means load multiple. So we can just write one instruction that's going to load a bunch of data from memory and consecutive memory addresses into registers. So in this case, the syntax is the first register, R10 here, is going to be your pointer register. So it holds an address. It will be assumed to hold an address by the assembler. In this example, it holds the address of 1000. So then we have in a list in curly brackets of 4 registers separated by commas, registers R0, R1, R6, R7. They do not need to be contiguous. They don't have to be R0, R1, R2, R3. They can be any 4 registers. However, they do have to be listed in ascending order. Writing this like R1, comma R7, comma R6, comma R0 would not be allowed. The assembler would create an error there. They have to be listed in order, but they do not need to be contiguous. So in this instruction is going to take the 4 words in memory starting at address 1000 and put the first word in R0, so the word that's stored at address 1000 is going to be put into R0, and then 1004 into R1, because every memory word is 4 bytes. So address 1004 goes into R1, 1008 into R6, 1012 into R7. Now the IA increment after means we increment the memory address after we've loaded. So that means if R10 holds 1000, then address 1000 is used to load memory R0, and then we increment it after. So then we increment it to 1004 and use that next address 1004 to load into memory, into register R1, etc., etc. You can also make this IB, meaning increment before, which means increment the address in R2 first and then use that address to load register R0. Okay? And there's also decrement after and decrement before. Okay, but in this particular instruction, we're assuming that the 4 values in memory that we want to load are at addresses 1000, 1004, 1008, 1012, and the exclamation mark means write back. It means update R10 such that it will now have 1016 in it at the end. If this wasn't here, then after this instruction is done, R10 would still hold 1000. It would use addresses 1000, 1004, 8, and 12 to load the registers, but then R10 would still have 1000 in it. When the exclamation mark is here, that means R10 has been changed each time to these values, and then finally it'll end up with 1016 in it. So you can write it with or without the write back. Okay, a few other, let's keep moving. Test instructions. We have a number of instructions in ARM whose sole purpose is to compare 2 numbers and then set the status bit in the processor's status register accordingly. So one thing we often want to do is check whether a particular bit in some data is set to a 1 or a 0. You'll recall that when we talked about input-output devices, we said that a keyboard will have a register in it called the keyboard status register. And when somebody has pressed a key on the keyboard, the keyboard will update that bit in the status register and set it equal to a 1. Now the CPU, when it's polling the keyboard, it will read that status register in the keyboard, and it will then check whether that bit has been set to a 1 or not. If it's been set to a 1, the CPU will know, there's new data waiting for me in the keyboard, I'm going to go get it. If it's set to a 0, the CPU says, there's still no new data, I'll try again later. So that's an example of where we want to test an individual bit in a word or in a register. So the test instruction allows us to do that, where we can test what's in one register with what's in another register or with an immediate value. So in this particular case, we are testing what's in R3 with the immediate operand 1, and it's done by a bitwise logical AND. That's what this instruction will do. So if register R3 looks like this, where we've got 32 bits, okay, the immediate operand 1 obviously looks like this, with all zeros like this. So when you AND 1 with what's in this register R3, okay, all of these zeros will cause all of this stuff to disappear when we AND. We don't care about any of these top 31 bits, but this one here, when it's ANDed with this bit, will give a result of whatever this bit is. If this bit is a 0, well then 0 ANDed with 1 will be 0. If this bit is a 1, 1 ANDed with 1 will give us a 1. Okay, so if this bit is equal to a 1, after this instruction, we will have a result, 1 ANDed with 1 is 1, which is not 0, meaning the Z bit in the processor status register will be set equal to a 0, because the result of this ANDing did not result in a 0. Okay, so Z is equal to 0 if this is a 1. If this is a 0, if this lowest bit in R3 is a 0, well then ANDing 0 with 1 will produce a 0, which will set the Z bit in our processor status register equal to 1. So now after this instruction, all we have to do is check the Z bit in the processor status register to see if it's 0 and 1, or 1. If it's a 0, that means we might want to do one thing. If it's set to 1, well, that means we want to do something else. Okay? So the test instruction is very valuable for checking what the status is of one individual bit. This one does not change the value of R3. R3 will still have in it what it had in it when this instruction started. The test if equal instruction is a little bit different. It actually will test whether the entire word is the same. So in this particular case, we're going to test to see if what's in register R2 is equal to the immediate operand 5. And it does that with a bitwise logical exclusive OR. You can try that on your own if you want to see how that works. But again, this instruction is going to set a Z bit. If R2 actually does have 5 in it, well then it's going to set the Z bit equal to a 1, because the logical exclusive OR of 5 with 5 is 0. So it will set the Z bit, the 0 bit, to 1, and you'll know that these two are equal. If these are not equal, if R2 does not have 5 in it, then the logical exclusive OR of something other than 5 with 5 will result in a non-zero value, which means the 0 bit in the processor status register will be equal to 0. So this will tell us, now we just have to look at the Z bit and we'll know whether these two things are equal or not. Okay. None of these change the value of R2. Same thing here. R2, its value will not be changed. Instructions available to us. And finally, we have what's called the compare instruction. So the compare just does a simple subtraction. It doesn't change either one of these registers. In fact, none of the same thing with the compare instruction. The values in these registers are not changed. They are simply differenced. Okay? And this will, again, update the condition code flags based on the result of this subtraction, whether it resulted in a 0 or if what's in Rn is smaller than what's in Rm, then this subtraction will result in a negative number. So the negative bit in the processor status register will be set to a 1. So we can check any bit we want in the status register to see what, if one is bigger than the other, if it's positive, if it's negative, if it's 0, etc. Okay, last thing I wanted to bring up that I talked about in today's lecture were two documents that I've posted on Canvas. ARM, and it's these ones that I focus on in lectures that you really need. So we're going to talk about these on our next lecture on Friday, and if you're familiar with. And so on Friday, we're going to look at how we can use some of these instructions in some example code. Okay, so that's basically a shortened version of today's lecture. We'll see you on Friday. To the end of this, I've got loaded here. There's two documents on Canvas. One is called the ARM reference, and it's a 3-page document. This is the first page, and it's basically a summary of the ARM instruction set. In the past, I've given students a copy of this during the midterm and final. I think I'm probably going to do that again. I haven't actually written the midterm or final yet, so I'll see about that. But we don't expect you to memorize every instruction in the ARM instruction set, but we do expect that you can, if you're given some code to read and you're not familiar with a particular instruction, you can come to this reference, which is only 3 pages long, to figure out what that instruction does. So in this ARM reference, you'll see that there's a number of columns here. There's a key to what these symbols mean, but the main part of it is this big table where we've got different categories of instructions. So these are move instructions, these are arithmetic logic unit instructions. On the next page we've got load instructions, store instructions, then some at the bottom that we're not going to worry about. To either this page, well, let's look at this page. In this table, you'll see that we have, again, the first column is different categories of instructions. The second column are individual instructions. So we're going to talk about branch instructions in the next lecture, but here we're talking about load instructions. And in the third, you'll see we've got the actual assembler syntax for these different instructions. So here you see our load register instructions that we've used a lot, okay? And you'll see our load multiple, which we introduced today, okay? And it shows you, here you can see the different suffixes you can add to the load multiple instructions: increment before, increment after, decrement before, decrement after, register RD, whether you can specify write back with the exclamation mark, and then the second operand is stored here, and it tells you a bit here what's actually going on, okay? So the simple load register instruction, we're going to load register RD with what this operand is here, right? And that's what it tells you to do here. So I highly suggest you take a look at this document on Canvas. It's called the ARM reference. It's only 3 pages long. You don't have to memorize it. You don't have to know what every instruction is on here, but you should familiarize yourself with it, because if you're going to use it on a midterm or a final exam, you don't want to spend your time in the exam figuring out how this table works. You want to be familiar with it as well. So that's what I'm recommending. Spend some time looking at this, and look for the ones that you've already known, like load register, store register byte, load register byte. We have here, right? We talked about that one today in our example, so have a look at that. The other document on Canvas is the actual full detailed instruction set for the ARM process for you. You don't understand anything here, you can. And then on the third page, we've got some other stuff that helps us figure out. We've got addressing modes, all the addressing modes that we've talked about in ARM. They're all listed here with examples of what the syntax looks like. Okay, and then some other stuff. Here is, increment after, increment before, decrement after, decrement before, that I talked about with the load multiple. Okay, there's different types here. But if you go back, it's 60. This 3-page reference isn't good. Look up, every page is long. It starts here. I don't expect you to read this, but if you're interested in how something is done in detail, or if the ref instruction in this 60-page instruction set reference document, if we look at the first few pages, here's a table that shows you the ARM instruction set formats. So these are the 32 bits for the different types of instructions. Here's a summary of the instructions. This is very helpful, okay? And their action. And then it tells you what section in this document where you can find out more information. And if we go there, more instructions, the condition field, we haven't talked about that, but let's go to maybe what I talked about in in the lecture today on October 6th. If we go back to here, the branch and branch with link instructions, we haven't talked about those. We're going to talk about those next with subroutines. It shows you what the instruction format is, and then it talks about the individual bits and what they do. That is basic, and then it shows you the syntax of how to use this instruction and some comments on what these fields are, and then it shows you some examples of how you would use these, would use these branch instructions in some code. Okay, so you can find more information there. All right, so